Hello and welcome to Bedroom Physics. Today I'm going to be talking about mechanical waves. There are mainly three types of waves. There are transverse waves, longitudinal waves, and waves which are a combination of both. Now, transverse waves is when the particles are being displaced in a vertical direction. Longitudinal waves are when the particles are being displaced in a horizontal direction. And sometimes, perhaps, if you have a container and it has an open top, and you get a plunger to push it, then you're going to get properties of both transverse waves and longitudinal waves. That is, the particles will oscillate in circles. Of course, the particles do not actually move through space in the sense that they will be in different positions as time goes on, but rather they're going to oscillate around some equilibrium point. But there are three really important things about waves that we need to know. Number one is that waves propagate with a definite speed through a medium, and that speed is determined by the characteristics of that medium. The second thing that we need to know is that that medium, like I said, does not travel through space, but rather the particles oscillate or revolve around some equilibrium position. And lastly, we input energy into a medium through mechanical work, and the wave transports that energy. That is, the wave does not transport matter, but it transports energy. But these are just wave pulses. What if we have a wave which has periodic motion? Well, in terms of a transverse wave, if you had an arm that was moving, let's say a string, up and down, it would create a wave with some wavelength, that is the distance between each crest, and that wave would travel that wavelength through some period t. However, it would be a little bit different for the longitudinal waves. Say you had some fluid in a tube and then an arm that pushes it back and forth. Now what's happening here is the arm is pushing the fluid, and as it's pushing, the region at the surface area of the arm is being compressed. That is, the fluid is increasing in density. And that region is going to push the next region of density over. And there's going to be a movement between these high density or high pressure areas and these low pressure areas. Of course, the low pressure areas are known as rarefactions, and they move along steadily through the tube over time, even as the arm is pushing. The way that we would find the wavelength is we would take the points when they are at the negative amplitude or the maximum negative value, and then we would take it when the points are at its maximum positive value, and they would be the distance between each rarefaction, as you can see here. This would be the distance of the wavelength. And of course, the wave, as you can see, would actually be described as the location of the points in a horizontal sense. Of course, the period would still be determined by the arm itself, but the amplitude, rather than the distance between the top of the arm and the bottom of the arm in the transverse wave, it would be the furthest point in the arm and the lowest point in the arm in a longitudinal sense. But there is a relationship to be made here. So we know that the wave from crest to crest is a distance lambda, noted by this symbol here. And we also know that the wave travels this distance lambda in some period t. And so we could find out the velocity that the wave is being propagated by using this relationship of the distance that it travels over the period. And so we're going to get velocity is equal to the frequency times lambda, and of course frequency is the inverse of the period. So when sinusoidal waves travel through a medium, the particles undergo simple harmonic motion around some equilibrium point. It's also important to remember, as we said previously, that the velocity is actually not determined by the frequency or the wavelength, but rather determined by the characteristics of the medium. And so if frequency gets larger, for example, then the wavelength will get smaller because velocity over the frequency is equal to wavelength. Of course, if the wave is already set and everything, and you just know information about the wave, then you could solve for the velocity using frequency times lambda. But how would we describe these waves mathematically? Well, we know that the waves, and this again is an example of some string, we know that the crest of the wave is at the amplitude, max amplitude, or positive amplitude, and the trough of the wave is at negative amplitude. So this wave is oscillating between some positive and negative value. And whenever we have something oscillating between a positive and negative value, we have trigonometry. And so we can describe this wave using y of xt as it's dependent on both the distance that it's at, the location of the particle, and also the time that goes by, because of course as times go by, the arm moves up and down. And so we get a, which is the amplitude, times cosine of 2 pi frequency times t. Of course, this is only for when x is equal to 0. So how do we connect x with this formula which only has t? Well, since the wave repeats, isn't it true that some point x here can be described as the same point x here at some other period of time? And so from this realization, we get y of xt is equal to a cosine angular frequency, which is 2 pi f, times t minus x over v. Of course, x over v is saying if you have a distance over the velocity, then you're going to get the amount of time that it took to get there. So then this is in terms of time, and angular frequency, of course, is radians over time, so time cancels out, and we're left with radians. Now, two important things that change from this equation to this official wave equation, you could say, would be that the relationships that we've noted is that cosine of negative theta is equal to cosine of theta. And, of course, we've also noted that 2 pi over lambda is equal to k, which is known as the wave number. And the way that we get this is, since this is 2 pi f, when we multiply the frequency, which is 1 over time, we cancel out the time from the velocity. And so we get x over lambda. And once f is gone, then we're just left with 2 pi. So we get 2 pi x over lambda, and of course 2 pi over lambda equals k, and so we get the following. One more important relationship is that the angular frequency is equal to the velocity times k. After all, if you divide through by 2 pi, you get v over lambda equals f. Now that we know these relationships, we can really start the fun. So we know that the equation of the wave is equal to y of xt, and it's equal to a cosine kx minus angular frequency t. Of course, this is a function for the position of the displacement in the y direction. So what if we took a derivative in terms of t? Wouldn't we get the velocity in the y direction? And so if we took a partial derivative, which means when you hold all the other variables constant, in this case x, except for the one we're looking at, which happens to be t, we're going to get angular frequency times the amplitude times sine of kx minus angular frequency t. And it's going to be equal to v of y, that is the velocity in the y direction. So the point is being displaced up and down, and so the velocity can be derived using this equation. If we take another time derivative, we're going to get the acceleration of that point, and it's going to be equal to negative angular frequency squared times the amplitude times cosine of kx minus angular frequency t, which is going to be equal to a of y. Now, if you took the derivative in terms of x, then you would get something that describes both the slope and the curvature of our wave. So if we look at the second derivative of y in terms of x, we're going to get negative k squared times a times cosine kx minus angular frequency t. But remember, we have the relationship that angular frequency is equal to the velocity times k, which means that angular frequency over k equals the velocity. And what do we have here? We have angular frequency and we have k. Of course, it is squared, so we're actually going to get velocity squared. So if we put the second derivative of y in terms of t, on top of the second derivative of y in terms of x, we're going to get v squared. This is known as the wave equation. One thing I would like to note about this part is that I am using cosine, but you could also use sine. After all, the only difference between cosine and sine is a phase difference. However, I do think that the cosine is a superior way to note the wave, because then you're just measuring the wavelength crest to crest instead of from 0 to next 0 or whatever it is that you're going to have to do. Now, I've said many times throughout this video that the velocity is dependent on the medium, the characteristics of the medium. Well, now let's prove that mathematically. So say you have a string and all of a sudden you apply a vertical force to it and you move one of the ends of the strings up. You're going to end up setting more and more mass in motion, and this point between the string that is still at rest and the string that is in motion is going to be moving at a constant velocity. Why is that? Well, the effect of the force that you're giving the string is going to be lifting more and more mass, so the velocity is going to stay constant. Additionally, the velocity upwards is also going to be constant. And the reason that is because of impulse momentum. An applied force times time is equal to momentum, which is equal to mass times velocity. And so we get the relationship f of y times t is equal to m times v of y. Of course, if we note here, this triangle made by f of y and f of x and its hypotenuse is similar to the triangle v of y times t and vt. Of course, v of y times t is a distance. This is the distance that the string will be after a certain amount of time. After all, it is moving at a constant velocity along with the velocity in the x direction. And so from this, we can get the relationship that f of y over f of x is equal to v of y times t over v times t. And when we multiply over t and f of x, we get f of y times t is equal to f of x times v of y over v times t. But we know that f of y times t is equal to the momentum m times velocity in the y direction. And so we're going to get f of x times v of y over v times t is equal to the mass times the velocity in the y direction. Of course, the mass is changing over time. And the way that we're going to denote this is by multiplying mu, or linear mass density, which is mass over the length, times the velocity in the x direction times t. After all, after a certain amount of time, the length that's being affected is going to grow, and so more of the mass is going to be in play. Now from this relationship, we can cancel out the t's, we can cancel out v of y, and what we're left with is v is equal to the square root of f of x over mu, or the linear mass density, or in other words, the velocity in the x direction, the velocity that the wave is propagating in on a string, that is equal to the square root of the tension of the string over the linear mass density of the string. Like I said, the velocity has to do with the characteristics of the medium, not the frequency or the wavelength. And from this, we can make a more general statement, which says that the velocity is equal to the restoring force that returns the particles back to equilibrium over the inertia that is resisting this return to equilibrium of the particles. Now, one more thing I would like to say about this portion is if we go back to our wave equation here, we'll notice that if this is positive, then the wave is going to be traveling at a different direction. After all, if we pull out k, we're going to get angular frequency over k, which is the velocity. And if the velocity was negative, this sign would become positive, even though the wave would be traveling in the negative x direction. Of course, this is just a mathematical thing. If you remember the slope equation, y equals mx plus b, if you have m times x plus 1, the 0 is going to be 1 to the left, and if you have x minus 1, the 0 is going to be 1 to the right. Now on to the next portion. So let's say you have a string and you pluck the string, and then you examine a point on a positive slope of the string. Like so. If we examine the actions around the point, we would see that the portion of the string to the left of the point would be exerting force to the portion of the string on the right of the point, and the portion of the string on the right of the point would be exerting a force on the portion of string to the left of the point. And we would also see that the vectors for force and the vectors for the slope would be similar. That is, the triangles would be similar. And so we will get the relationship f of y over f of x is equal to the slope of the wave function, except it's negative. After all, the slope is positive, but the vector of the f is the other direction. Let's also keep in mind that omega is equal to vk, and v is equal to the square root of f of x over mu. So we have f of y over f of x, and the point on the string does not move in the x direction. However, there is displacement in the y direction, and there's a force in the y direction, which means that the force is doing work on that point. And if we're doing work, then we have power. And so we can solve for power by doing p of xt is equal to f of y of xt times v of y of xt. Why f times v? Well, power is equal to joules over seconds, and joules is a force times distance. So we have force times meters over seconds, and so we're going to have force times distance over seconds. Eventually what we're going to get is f of x times k omega a squared sine squared of kx minus omega t. And it's important to note that power cannot be negative. It is either 0 or some number above 0. Now, if we plug in our values here, our final formula will be the square root of f of x times mu times omega squared times a squared times sine squared of kx minus omega t. Of course, p is at max, power is at max when sine is 1, and what we're going to have is just the coefficients. We could also solve for the average power, which is going to be half of the power maximum. However, not all waves travel in a single dimension. Sound or seismic waves travel in all directions. In this case, we're going to have to use intensity, which is going to be power over area. And as you can see, intensity is subject to the inverse square law, as the radius is squared in the denominator. But let's say you're using the same amount of power in a different amount of area. Well, if P remains the same, I of course would be different because R is different, but we could multiply A over. And it doesn't matter what the intensity is, we could set them equal to each other. So for example, I times 4 pi R1 squared is equal to I2 4 pi R2 squared. 4 pi's we cancel out, and eventually we'll be able to get the ratio that the first intensity over the second intensity is equal to R2 squared over R1 squared. Okay, now we've talked about power in a wave or energy in a wave. Let's move on to interference, boundary conditions, and superposition. Let's say you have a string, and on the other end it's fixed to a point. You send a pulse, and it travels, hits the wall. What's going to happen? Well, the wave is going to travel, it's going to flatten out, and then it's going to invert. Why is this going to happen? You see, as the wave is traveling, when it hits the wall, it's going to apply a positive transverse force on the wall, and the wall is going to apply a negative transverse force on the string. And so the wave is going to hit the wall and then reflect inverted all the way back the way it came. However, what if the other end of the string wasn't fixed? What if it was free? Well, we would send out a pulse, the wave would hit the wall, but there would be no negative transverse force. So the end of the string will keep going until it reaches a maximum, typically when the string is fully stretched, and it will stop there for a moment. However, the tension from the fully stretched rope will bring the string back down, and it will reflect the pulse back where it came from, except not inverted. Now, a similar thing happens when you send two waves against each other. Take, for example, one wave going against an identical wave which is inverted. This wave is inverted and is going to the right, and this wave is inverted and going to the left. They will travel, and then once they're right on top of each other, since they are identical, they will cancel out, and then they will continue traveling. Note how at this point, there is no displacement in the y direction. This is known as the principle of superposition. The total displacement of a wave is equal to wave 1 plus wave 2. That is wave 1 plus wave 2. If, for example, the waves were coming at each other and neither one of them were inverted, then they would continue, and then they would get amplified by the sum of the two amplifications, and then they would continue. Note how this point would no longer have a zero y displacement. However, the slope would be zero even at the top of the hill. But now let's say we have a periodic wave and the other end is at a fixed point and it keeps coming back. Let's analyze what happens then. Well, if we have our wave and it's being sent towards the right and then it's being reflected, when they are in phase and at opposite magnitudes, then the string, which is represented by the white line, will be flat. However, let's say that the amplitudes of the waves match up. Well, then the string is going to have an amplitude equal to 2a. And notice, we still have these points which don't move. We have one at the beginning of the wave, halfway through the wave, and at the full wave. These are known as nodes. In contrast, the points in which have the most displacement in the y direction are known as antinodes, and these happen every half wavelength starting at pi/4. The equation for these waves, or better known as standing waves, would be equal to the superposition of the two waves. Ultimately, through a cosine identity, we will see that they equal to 2a times sine kx times sine omega t, and 2a is actually known as the amplitude of the standing wave. It's important to note, however, that standing waves do not actually transfer any energy. Consider that one wave is going one direction. It is transferring energy one direction, and the other wave is inverted and transferring energy in the other direction, meaning that the average energy transmitted is going to be zero, and therefore the average power is going to be zero. The last topic of this video is going to be normal modes on a string. Say you had a string and it was fixed at both ends, and then you pluck it or whatever, and it sends a wave throughout the string and it reflects itself. Well, the wavelengths that could form would be the lengths of the nodes. That is, every node happens at half a wavelength, so our wavelengths are going to be lambda over 2, lambda, and 3 lambda over 2. Of course, if we note here, we can see that there's a relationship between the length of the string and the wavelength. You see, half a wavelength is equal to one length of the string. Or you could say that one wavelength is equal to 2 lengths of the string. Here, we see that lambda is equal to the length of the string, and on the third one, we see that lambda is equal to 2/3 of the length of the string. There is a pattern here, and that pattern is lambda of n is equal to 2l over n. Here we have 2l over n when n is 1. Here we have 2l over n when n is 2. And here we have 2l over n when n is 3. N, however, is a positive integer. You may know this as the harmonic series. If you were to find the frequency of this, that is velocity over the wavelength, you'll see that f of n is equal to n times velocity over 2l. Each n is called a normal mode, or in music, we can call these harmonics. When n is equal to 1, that is the fundamental frequency. Any n after 1 is called an overtone. Now there are two last things that I want to say about mechanical waves. Number one, that there can be wavelengths that are not exactly at the nodes. However, these wave patterns won't be steady. And number two, this is all really one big ideal situation. In truth, for example, when you pluck a string on a guitar, a lot of times a single harmonic is not going to happen. That is, a single wave pattern is not going to happen. Typically, it's actually a superposition of wave patterns. That is, it might be the fundamental frequency and also frequency 2, 4, and 5, or 2, 3, and 4, whatever. And in order to analyze a wave like that, you will need to use Fourier analysis. In any case, this has been the concept video for mechanical waves. I hope to see you in the example video.